Good morning. Welcome back to MAC2311, section 002, calculus 1. We're about a week. Sorry, just 1 second. Okay, you got to pick what you want, all right? What was I saying? We're about 2 weeks in, and today we're going to talk a little bit more about limits and continuity. And then we're going to talk about limits at infinity. So we've got quite a bit to cover. I'm going to come over here. I do have a couple of announcements before we get started today. So let's get to it. All right, first things first. Monday is the 18th. There will be no class. Because it's Dr. King's birthday. Sorry, let me get this to focus. So the college is closed in honor of Dr. Martin Luther King's birthday. And since that is a class day for us, normally that Monday would normally be a class day, it's important that we remember that there is no class on that day. The college is closed, and since this is a synchronous class rather than an asynchronous online class, we have to abide by the college's rules. So take the day off to remember Dr. King and all the amazing things he did. Another announcement-y thing, today's office hour is getting pushed to like the 4 to 5 hour, maybe even a little later. I know this kind of sucks, but I have to go look at a house. The appointment to go look at the house, I think, is at like 2 p.m. So I'm thinking I'll probably be back done with all of that stuff by 4 at the latest. So today's office hour is going to get pushed back to 4. If it does end up having to be later, I have the Canvas Teacher app on my phone, and I'll post an announcement updating that. But it's worth making a note of, so you don't come looking for me in the office hour link and then not find me and be like, what the fuck, where is he? So today's office hour is going to be 4 to 5 p.m. and I will post an announcement later in the day if I need to modify that. All right. So what are we doing today? We've been playing around quite a bit with limits, but I want to talk more about continuity, which remember is section 2.5. And I want to talk about limits at plus and minus infinity, which is section 2.6. So everything that we do in this class is built out of limits. I've said that a bunch of times. Obviously, the continuity stuff is built out of limits. The definition of being continuous at a number A is in terms of limits. Limits at infinity kind of feel like a weird jump because they're not immediately connected to any of the things we've been doing. But it fits here for a few reasons. First off, we're learning about limits now. So even though none of what we've done so far had to do with sending x to infinity or negative infinity, we've been sending x to different places. So it kind of makes sense to see all the places we can take limits at once. Another thing is that later in the semester, we're going to build these things called Riemann sums. And if you or a friend is taking Calc 1, Riemann sums are one of the things that Calc 1 students tend to complain about a little bit. Understandably, they're very notation dense. The better you understand section 2.6, the easier the Riemann sum stuff will be when we get to it. So it's worthwhile to invest the time now, and that way you can focus on other things down the line, things that are meant to be focused on. But first, I'd like to look at a problem or two relating to continuity. Now, last time we finished with that piecewise continuous function. And I asked you guys to try and sketch the graph. Last time we finished with an example talking about the function f of x equals, it was x squared minus 3x over x squared minus 9 for all x's not equal to 3. And it was defined to be 1 at x equals 3. And I said we should try to draw the graph of this function. We deduced using the limit definition that this function is not continuous at 3. We showed that the limit as x goes to 3 of f of x, which is the limit as x goes to 3 of x squared minus 3x over x squared minus 9 was equal to the limit as x goes to 3 of x over x plus 3, which is 1/2. And since f of 3 itself is equal to 1, the function f of x is not continuous at x equals 3, right? This was the basic result from last time when we worked on this. We said that, when you're taking the limit as x goes to 3, we're not interested in x being exactly equal to 3. We're interested in x is getting closer and closer to 3. So we used this portion to take the limit. And then we did some factoring and canceling, top and bottom here, and that got us this thing. And now in this thing, we were able to take the limit just by plugging in, and we got 1/2. Now, since the piecewise definition of the function has f of 3 equal to 1, and the limit as x approaches 3 of f of x is 1/2, the limit as x approaches 3 of this function is not the same as f of 3. And that's exactly the definition of continuity. Remember, a function is continuous at a if the limit as x approaches a of f of x is equal to f of a. So we would need this thing to be equal to this thing for this function to be continuous at 3. And since those are not equal, since 1 is not equal to 1/2, we said that this function isn't continuous at 3. And I asked you guys to draw the picture. So you've had some time to think about it, maybe some time to work on it. I'd like to go ahead and draw for you this picture. We know that after factoring and canceling, this thing is x over x plus 3 if x is different from 3, and 1 if x is equal to 3. So if I want to graph this, the problem is just to graph this function, then everywhere besides at 3, it's going to look like this. So do we know what the graph of that thing looks like? So graphing rational functions, this is something that's in every pre-calculus class, even here at Santa Fe with our not so stellar pre-calculus sometimes. Graphing rational functions is a part of that. There's a bunch of things you can do, right? You can find vertical asymptotes and the domain. Those come from setting the bottom equal to 0. So we learn, okay, this thing has a domain issue at 3. Good old-fashioned x over x plus 3, if we just focus on that for the time being, he has a vertical asymptote fuck me. He has a vertical asymptote at -3, where that bottom is 0. Vertical asymptote where the bottom is 0. And then if you set the top to 0, you'll find that he has an x-intercept when x is equal to 0. And what else? The horizontal asymptote we can figure out by taking the limit as x goes to infinity that we haven't talked about yet, but you remember from pre-calculus that if the degree of the top and the degree of the bottom are the same, then the horizontal asymptote should be the ratio of lead coefficients, which in this case is 1 over 1. And once you have this framework, you can generally draw a pretty good picture. So over here, this function is going to look like this. Oh, I drew up on the other page there, didn't I? All right, that's fine. And then in here, we're going to have something like this. Now I'm going to stop before I draw this next branch and mark off x equals 3. The limit as x approaches 3 of f of x is 1/2. So we're going to have this sort of behavior in here. And then if I want to graph the piecewise function itself, remember the function value was defined over here to be 1. So this is the graph of this function. It's a hyperbola, and the branches of the hyperbola over here and over here really should be the same size. I'm just zoomed way in on this piece, so I don't have a lot of room to draw over here. They should be scaled similarly, but we had this hole here, and that's coming from the piecewise definitions now. This fella is after I did the factoring and canceling, so it's a little bit hard to see. It's a little bit harder to see what this graph will look like from the original expression that was here, from x squared minus 3x over x squared minus 9. But after we clean that up algebraically, we'll be able to draw the graph of this thing pretty readily. This is something we should remember how to graph from pre-calculus. And you can see, so I wanted to draw this picture so we can start connecting the limit definition of continuity to the sort of pre-calculus understanding of continuity. We can see that this function has 2 discontinuities, and I'd like to talk about the types of discontinuities they are. What's going on over here at x equals -3, we have an infinite discontinuity. Right? Because the function is blowing up to plus infinity or minus infinity, depending on the side you approach from. We would say here, the limit as x goes to -3 from the left of f of x is plus infinity. The limit as x goes to -3 from the right of f of x, this is negative infinity. And this is something we talked about earlier in the week. Hopefully we're all comfy with that. Because if I'm a little dude walking along this graph, as I approach -3 from the left, kind of with my feet glued to the graph, I'm going to fire up through the ceiling. And as I approach -3 from the right, with my feet stuck to the graph, I'm going to drop through the floor. So we're going either all the way up to plus infinity or all the way down to minus infinity, depending on the direction we come in from. So the overall limit here, we would say, does not exist. But from the left and from the right, we have these infinite limits, and that corresponds to this vertical asymptote. Over here, though, this is a different kind of discontinuity. This is called a removable discontinuity. Because we could fix the discontinuity, we could make this function continuous just by taking this dot and moving it back down here. Right? So by reassigning the function value at one point, we can make the discontinuity go away.
Sorry, quick question. For the limit you just wrote down for it does not exist, is it supposed to be -3 or +3?
-3. -3, because we're over here working at -3, right?
Okay. Oh, wait.
Oh, did I leave the negative off here? I'm
okay,
sorry.
just wanted to check. Thank you.
Oh, good catch. Thank you very much. Yeah. Okay, and this one is called removable discontinuity because we could fix the discontinuity by changing the definition of f of 3 from f of 3 equals 1 to f of 3 equals 1/2. There's one other type of discontinuity that we will encounter often, and those are called jump discontinuities. So I wanted to show you the two kinds of discontinuities this function has, and then I'll show you one other kind. There was a question in chat, where did the -3 come from? So I want to make sure I'm answering the question that you're asking, Fabrice. I wanted to graph this function, right? This function that we were working with last time. And the weird behavior at -3 is coming from the factor of x plus 3 in the denominator of this piece here. So I can open up in Desmos if we want to look. If we graph just x over x plus 3, sorry, this is my Calc 2 class yesterday. If we graph just x over x plus 3 on the appropriate size window, you'll see that he does have this discontinuity, this vertical asymptote here at x equals 3. Right. So that's what I have right here, is this vertical asymptote at -3. And you can kind of see what I mean by the branches of the hyperbola being scaled the same. I just ran out of space up here. Well, so vertical asymptotes, yeah, this is what we're getting at, right? Is that vertical asymptotes are a type of discontinuity, right? This function is definitely not continuous at -3 because, look here, the limit as x approaches -3 does not exist. Remember the definition of continuity. A function is continuous. I should say this again just to make sure we've said it today. Recall f of x is continuous. I'm going to abbreviate continuous as CTS at x equals a, means that the limit as x approaches a of f of x is equal to f of a. Right? So we have to ask, is this satisfied at x equals -3? All right, if you plug in -3 for a in this expression, do you get a true statement or not? If this statement is true when you plug in -3 for a, then we would say f of x is continuous at -3. I claim that this statement is not true when you plug in -3 for a, because the limit as x approaches -3 of f of x, this part does not exist. And if something does not exist, remember we talked about the 3 ways this definition can fail. Either the limit might not exist, the function value might not exist, or they might both exist but not be equal. Over here, the limit does not exist because the limit from the left is different than the limit from the right. The limit from the left is plus infinity, the limit from the right is negative infinity. So a vertical asymptote will always be a discontinuity. horizontal asymptotes are not connected to the idea of discontinuity at all. It's just a good idea to draw a horizontal asymptote for a function when you're graphing it, if it has one, right? If I wanted to draw a nice graph of this function, it absolutely should have the vertical and horizontal asymptotes included. This is just how we graph things. All right, so here would be a good picture of this function. Now, the horizontal asymptote doesn't have anything to do with discontinuity. It's a total coincidence that this dot is at the same height as the horizontal asymptote. If that dot were up here, I would still have a removable discontinuity at 3. The problem here, so let me see, at x equals -3, we can check is lim x to -3 f of x equal to f of -3. Well, there's a problem here. Neither of these exist. F of -3, this is undefined. And this thing, this limit does not exist. So f is not continuous at x equals -3. Separate from that, we can check at +3. At x equals +3, we can check the limit as x goes to 3 of f of x equals f of 3. Is this a true statement or not? Well, here the limit as x approaches 3 of f of x, this is 1/2, and f of 3 itself is 1. But these are not equal. But this is not true. 1/2 is definitely not the same as 1. So f of x is not continuous at x equals 3. This is what we mean by checking one point at a time, right? You just have to investigate whether or not that definition holds at any given x value. So in answer to your question, Mackenzie, vertical asymptotes will always be discontinuities. They'll always be infinite discontinuities. But horizontal asymptotes have nothing to do with continuity. It's just a coincidence that this dot is at the same height as the horizontal asymptote. Okay, do we feel like we fully understand this example? Are there any questions about this example?
If one side of the graph goes to infinity and the other side is like defined, then is it infinite or is it jump discontinuity?
It's a good question. So there are some sort of weird behaviors that can happen. And your book, and indeed one of the homework problems I assigned, talks about continuous from the left, continuous from the right. So let me go ahead and introduce those ideas. One-sided continuity. All right, this is something that I will not harp on this a lot, but there's one homework problem I gave you where I want you to think about this stuff. If f of x is not continuous at x equals a, but the limit as x approaches a from the right of f of x is equal to f of a, then we say f of x is continuous from the right. And if the limit as x approaches a from the left of f of x is equal to f of a, then we say f of x is continuous from the left. So if from one side things appear to be okay, right? Like maybe you blow up to infinity on the left, but as you come in from the right, everything looks okay. The limit as x approaches a from the right exists. and is equal to the value of the function there, then we would say that you're left continuous or right continuous, but you're still not continuous overall, right? So I think the question there was what if we have something, and this is a fairly pathological example, I wouldn't expect to run into a lot of these, but what if I have something like this? I'm going to blow up to infinity here, but maybe, maybe I have fairly normal behavior from this side, right? Something like that. And this is filled in here. And we'll call this 1, we'll call this 2. So here, if this is the graph, y equals f of x, it's x. Here, the limit as x approaches 2 from the left of f of x is equal to infinity. And so I would say that there's an infinite discontinuity here. Right, the graph is definitely not one connected piece. It is discontinuous. And the function is blowing up to infinity. So we would say, just to be clear, f of x has an infinite discontinuity at x equals 2. But if you just look on what's happening from the right, the limit as x approaches 2 from the right of f of x, this limit does exist. The one-sided limit here does exist. It's equal to 1. And that's also f of 2, right? So I've defined the function at 2, even though it blows up to infinity from the one side, I've got a filled in hole here. So f of 2 does exist. F of 2 is the height of this hole. It's equal to 1. So we'd say f of x is continuous, but only from the right. At x equals 2. And this is a sort of subtlety that like I said, I don't want to beat you guys to death with, but I do want you to spend a little bit of time thinking about. Does that sort of answer your question?
Yes, sir.
Okay, cool. Yeah, this sort of thing can be neat. Vertical asymptotes can be a little bit weird. Usually we encounter them when we study rational functions. And if you're dealing just with a rational function, those guys will never be defined at their vertical asymptote, right? You'll always just see it like blowing up to infinity on the left and maybe negative infinity on the right, or maybe positive infinity on both sides. But if you start making piecewise combinations of rational functions, if you allow me to start kind of splicing rational functions together with other functions using piecewise tools, then you can encounter this sort of behavior. And it's an interesting thing. So we like to have the language to describe it. I wouldn't call this a jump discontinuity. I would still call this an infinite discontinuity, because on the one side, the function is still blowing up to infinity. So if either the left or the right limit is infinite, then I would say that that is still an infinite discontinuity. But jump discontinuities are a thing. And that's actually the last thing I wanted to talk about before we move on from our discussion of continuity. I'll leave this here just for a second in case anybody's still writing, but then we're gonna classify discontinuities. So theorems, right? Moving along. Types of discontinuities. We saw a removable and an infinite discontinuity. There's one more possibility, and those are called jump discontinuities. So I'm going to draw a graph here that has all three. If you have some behavior like this, this would be a jump. This would be removable. And anything like this would be an infinite discontinuity. So if I call this function f of x, then f of x, as drawn here, has a jump discontinuity at x equals -2. And jump discontinuities are ones where the left limit and right limit are both finite, but they're not equal. Right? Both of those limits exist, but they're not equal to one another. They're both finite, they both exist, but they're not equal. We have a removable discontinuity. At x equals 1, because here the limit exists. Right, this is, I'll call this 1, I'll call this 2. Right, so the limit exists, meaning those two one-sided limits are both finite and they both agree with each other. But those two things do not agree with the value of the function. And then at 3 we have, I'm sorry, yeah, at x equals 3 and item number 3 have an infinite discontinuity at x equals 3. Because here the limit as x approaches 3 from the left of f of x is infinity. And even if the limit from the right was not negative infinity, even if you just had an infinite limit on one side, that would be enough to say there's an infinite discontinuity there. But here it's also the case that the limit as x approaches 3 from the right is infinite. It's just negative infinity. Okay. So these are the different types of discontinuities that we're going to encounter. Number 1 is a jump discontinuity. Yeah, at -2 over here. Right here we have a jump discontinuity because the graph kind of makes this jump. And that's where the left limit and the right limit are both finite. Both exist and are finite. They're just not equal to each other. Right? The left limit and right limit both exist and are finite. They're just not equal to one another. And then a removable discontinuity, like we have at 1, is where the overall limit at 1 does exist and is finite, right? The limit as x approaches 1 here of f of x does exist. It is 1. It's the y value of this whole. but that's not equal to the value of the function there. The value of the function up there is 2. We call these removable because you could get rid of the discontinuity just by picking up this dot and moving it back down here. Right, that would fix the discontinuity. That would make the function continuous at 1. So this discontinuity here could be removed just by adjusting the height of that dot. And then at 3 over here, we have an infinite discontinuity. Okay. So we're at a place where I want to talk about a couple of kind of interesting notation things. We're hopefully getting used to slinging these infinity signs around a little bit. I'll give just a few seconds for people to write. Okay. So we're getting pretty brave with our infinity symbols. It turns out, in a lot of ways, calculus is all about wrapping your head around infinity. And that's not an easy thing. Just ask Georg Cantor. So infinity is complicated. Ask Georg Cantor. Cantor was the first man to try and really carefully look at what infinity is. I know the focus is drifting again. It'll come back. He was an early 20th century mathematician working around the time of Einstein and Riemann, late in Riemann's life. Leo Boldwick, if you're familiar with the entropy guy from physics, around the same time. He went totally batshit crazy, working on some problems about infinities, and really cool stuff he wrote. His book, The Mathematics and Philosophy of the Infinite, is one of the most important books of the last 100 years. We've noticed things like, if you think about the graph of f of x equals 1 over x, let me call it 1 over x squared just for fun, because that goes up to plus infinity on both sides of 0. Yeah, another graph we should know is 1 over x squared. The limit x goes to 0 of 1 over x squared is infinity. And this is why people may say things like 1 over 0 equals infinity. Now I'm going to put this in some quote bunnies here, right? It's like 1 over 0 equals infinity. This is my symbol for I don't take responsibility for this shit. It's not quite kosher, but it has some intuitive appeal. Because as you get closer and closer and closer to 0 on this 1 over x squared graph, the bottom is definitely getting closer and closer to 0. The top is staying 1, and clearly the y values are going up to plus infinity. So something like 1 over 0 equals infinity is appealing, has some intuitive appeal, even though it's not entirely rigorous. I would like to introduce the idea that 1 over infinity is also 0. Looking carefully at this graph, if we walk further and further to the right, the y values get closer and closer to 0. Right? I can show you more of that graph, the 1 over x squared graph. But as we walk further and further to the right along the graph, y equals 1 over x or 1 over x squared, the y values get closer and closer to 0, right? Here's 1 over x squared. As I meander off to the right, going further and further and further in this direction, those y values get closer and closer and closer to 0. So I want to say, sorry, my cat is scratching at the door, that the limit as x goes to infinity of 1 over x squared is 0. Right? The idea there being, you imagine walking further and further and further off to the right, these y values really do get closer and closer and closer and closer to 0. So we're getting into section 2.6. Before I introduce the material formally, this is why people say things like 1 over infinity is 0. And again, quote bunnies here, not entirely reasonable, but pretty close to reasonable. More reasonable ways to interpret these two statements. This bottom one here, if you take 1 and you divide it by a very, very, very big number, you will get something very, very close to 0. And over here, if you take 1 and you divide it by something very, very, very close to 0, you will get a very, very, very big number. All right, these are the sort of more rigorous interpretations of these two statements. And the bottom one is the one I'm going to focus on because we've seen shit like this first one, right? This is something we've been actually playing with a little bit now. But I'm going to get into section 2.6, which is where we're going to make rigorous those bottom statements. So these are limits as x goes to plus or minus infinity. So what are we saying here? Definition. If the y values on the graph y equals f of x can be made as close as we want, as close as you want to the number L by taking x to be bigger and bigger, then we say that the limit as x goes to plus infinity f of x equals L. This is our definition for a limit at plus infinity. And if you turn it on its head, similarly, if the y values on y equals f of x can be made as close as you want to L by taking x to be bigger and bigger in the negative direction, then we say that the limit as x goes to negative infinity of f of x is equal to L. So these are the definitions. And I'm going to give you a slightly more intuitive way to think about this. But first, I want to make sure you get these down. As close as you want. So as close as you want to L by taking x to be larger and larger. So Imagine you say, I want to get within like 0.01 of L. If you can manage that by making x bigger and bigger, then we would say that the limit as f of x, limit as x goes to infinity of f of x equals L. As long as you can do that for any boundary, right? 0.01, 0.001. Let me, I'll hold here, take a second to just write down, but yeah, these words here are as you want to L. This idea of as close as you want is math speak. It's a way of getting around a weird inequality. Another term for this is arbitrarily close. If you can make the y values along the graph of f of x arbitrarily close to L by taking x to be bigger and bigger, then we say lim x to infinity f of x equals L. Really, another kind of the most intuitive way I can describe this is if as x gets bigger and bigger and bigger, the y values along f of x get closer and closer to and stay closer and closer to L, then we say the limit as x goes to infinity of f of x equals L. In other words, the line y equals L is a horizontal asymptote. Right? Limits at infinity are the same thing as finding horizontal asymptotes. That's really what's going on here. Okay. Yeah, I do. Sorry, guys. Give me just 1 second. Okay. Okay. I stole a copy from my wife this morning. Okay. So here's one of my favorite example functions.
Somebody said they wanted you to go back.
I'm sorry, say that one more time.
Someone in the chat said they asked if you can go back.
Yeah, I can hold here for just a second longer, but then we do have to move. And I'll give about 15 more seconds to write. All right, we ready? So, watch out for me, Bones. Yes, I know you're cute. Watch out, Bones. So this function has a graph that looks like this. You may recognize this. Actually, no, you wouldn't recognize this as the derivative of the inverse tangent function. Not yet, but eventually. All right. Now, as I wander off further and further to the left and right, the y values on this graph are getting closer and closer to 0. The max height here, this is the point up here is 0, 1. It's our y-intercept. If I am a little dude walking along this graph, and I say, all right, I'm not trying to go towards any particular point. I'm on a journey. I'm going to go way the fuck out along this graph. All right, maybe I've determined to wander as far away from the y-axis as I can. As I walk further and further to the right, my y values get closer and closer to 0. So here I would say that the limit as x goes to plus infinity on 1 over x squared plus 1, that limit is 0. And similarly, if I had someone who really hated me, and as I was walking as far as I can to the right, they were walking as far as they can to the left, our y values here, these are also getting closer and closer to 0. So here we would say the limit as x goes to negative infinity of f of x, in this case, sorry, the function is 1 over x squared plus 1. Here, this is also 0. And what you notice is that this function has a horizontal asymptote, y equals 0, that it approaches on both sides. So limits at infinity and horizontal asymptotes, same thing, literally the same thing. Every time you were asked to calculate or find a horizontal asymptote in one of your previous classes, you were finding a limit at infinity. And now that we're talking about finding limits at infinity, you can lean on the stuff you learned about horizontal asymptotes in your previous classes, if you remember them.
Do horizontal asymptotes create discontinuity?
No,
Sorry.
no, horizontal asymptotes have nothing to do with discontinuity. Right? This function is continuous everywhere. In fact, we can use one of our theorems to prove that this function is continuous everywhere. Right? This is a rational function. It's a ratio of two polynomials. And we proved that polynomials are continuous everywhere in their domain. And since the bottom here is never 0, this rational function is continuous everywhere. Right? The only way for a rational function, a ratio of two polynomials, to be discontinuous is if the bottom is equal to 0. And then the only place they're discontinuous is at that point where the bottom is 0. So this function is continuous everywhere. And the horizontal asymptote is independent of any questions of continuity. Vertical asymptotes are connected to the idea of discontinuity, but horizontal asymptotes have nothing to do with being continuous. Okay, so here's a fact. The function f of x has horizontal asymptote has horizontal asymptote y equals L means the same thing as saying lim x to infinity of f of x equals L, or lim x to negative infinity f of x equals L. And it's possible for a function to have two different horizontal asymptotes, right? So it could approach one horizontal asymptote as x goes to plus infinity, could approach some other horizontal asymptote as x goes to negative infinity. But limits at infinity are the same thing as horizontal asymptotes. And then I have a theorem for you, and then we're going to do some calculation. The words after the here, same as saying. So the function f of x has horizontal asymptote y equals L, means the same as saying lim x to infinity f of x equals L, or lim x to negative infinity f of x equals L. This should have some intuitive appeal, right? Horizontal asymptotes are lines that the function gets closer and closer to as you wander off to the left or to the right. Well, if the function gets closer and closer to L as x wanders further and further off to the right, that's precisely our definition of the limit as x goes to infinity of f of x equals L. All right, so these definitions, the definition of horizontal asymptote and the definition of limit at infinity are the same definition. They say the exact same thing. The word or here is being used as it's used in logic. It's a non-exclusive or. It means this could be true, or both could be true. Okay. I do have to move. We gotta keep up pace here. If you do need to correct your notes, please consider going and rewatching the video if you need more time. But here's a neat theorem. If R is a positive real number, then the limit as x goes to infinity of 1 over x to the R is 0. And as long as it's not causing domain issues, the limit as x goes to negative infinity of 1 over x to the R will also be 0. Intuitively, this is pretty satisfying. As x goes to infinity, x to the R will get bigger and bigger and bigger because R is a positive power. So as x gets bigger and bigger and bigger, x to the R gets bigger and bigger and bigger. If you divide the number 1 by bigger and bigger and bigger numbers, you get numbers that are closer and closer and closer to 0. And the same is true as x goes towards negative infinity. As x goes towards negative infinity, x to the R is going to become very, very large. It might be very, very large negative or very, very large positive, but it's going to be big. And you divide 1 by a very, very big number, you will get a very, very small number. This theorem is one of our main tools for taking the limits at infinity. I'm going to show you how we use it. This example is going to be an example of what we call the renormalization trick. Renormalization is a word I steal from physics, where they kind of set the speed of light to 1 and then divide through everything in all their calculations by the speed of light. Right, so you just divide through everything by c, and it renormalizes your calculations to make things a little bit easier. And this renormalization trick is a trick for calculating limits at infinity. Okay, so I would like to take the limit as x goes to infinity in the expression x squared plus 2x minus 1 over x squared plus 4. You can try sort of plugging in infinities. But if you do that, you get, infinity squared plus 2 times infinity minus 1 all over infinity squared plus 4. Really not helpful, right? Really doesn't tell me shit. But what will tell me something is if I divide top and bottom by the largest power of x. That's the renormalization trick. In general, you divide top and bottom by the fastest growing term. X squared grows faster than 2x, and both of those grow faster than 4 or -1. The fastest growing term is therefore x squared. So my renormalization trick is to divide top and bottom by the fastest growing term. So I'll have upstairs here x squared plus 2x minus 1, and I'm going to divide by x squared, which means I'm going to multiply by 1 over x squared. And downstairs, I do the same. I am renormalizing this expression. Now, when I distribute that 1 over x squared in the top and the 1 over x squared in the bottom, when I divide every term by x squared, I get 1 plus 2 times 1 over x minus 1 over x squared, all divided by 1 plus 4 times 1 over x squared. Is everybody following the algebra? Okay. Now, according to my theorem, right, my limit laws all work great for limits at infinity. All those laws we had work just fine. So I can take the limit here by taking the limit of each of these little pieces on their own. That's what the limit laws tell us, right? Is that you can jump in here and give the limit to each of these little pieces on their own. As x goes to infinity, what happens to the pieces? One over x and 1 over x squared. Right? Because everything else here is constant. This is constant, this is constant, this is constant. The only non-constant pieces are 1 over x and 1 over x squared. Well, the limit as x goes to infinity of 1 over x is 0. That's what this theorem's telling us. And the limit as x goes to infinity of 1 over x squared, now here is this theorem with r equal to 2. That's also 0. So this limit over here is 1 plus 2 times 0 minus 0 over 1 plus 4 times 0. And that's 1 over 1, which is 1. Word here is pieces.
I'm lost.
So where do I lose you?
At the where it has like where you're explaining as x goes to infinity what happens to pieces over to the right.
So you're comfy with the algebra that gets us here?
Yes, I'm comfortable with that. I'm just confused on explaining what happens.
All right. So my goal is to take the limit as x goes to infinity in this expression. We're comfy with that, right?
Yes.
The only pieces that change as x changes are these 1 over x and 1 over x squared pieces, right? Everything else is constant. So if we wanted to, if that's doing too much at once, let's come in here with our limit laws. Remember our limit laws, we say we can split the limit up top to bottom. So this would be limit x to infinity, 1 plus 2 times 1 over x minus 1 over x squared, all divided by limit x goes to infinity, 1 plus 4 times 1 over x squared. And then I can give the limit to each of those pieces on their own. So I'd have limit x to infinity of 1 plus 2 times limit x to infinity 1 over x minus limit x to infinity 1 over x squared, all divided by limit x to infinity 1 plus 4 times limit x to infinity 1 over x squared. This is me applying the limit laws from earlier in the week to this expression here after we renormalize. So the pieces that we need to figure out are this piece, and this piece. Everything else is easy, right? The limit as x goes to infinity of 1, that's just 1. It's a limit of a constant function. Limit as x goes to infinity of 1, this is just 1. It's a constant function. So these 3 pieces in the blue box, those are the hard pieces to figure out. But if you refer back to this theorem, if r is any positive number, then the limit as x goes to infinity of 1 over x to the r is 0. Well, this is 1 over x to the 1 as x goes to infinity. This is the limit as x goes to infinity of 1 over x to the 1. This is the limit as x goes to infinity of 1 over x to the 2. This is the limit as x goes to infinity of 1 over x to the 2. These are all 0 by the theorem.
So as long as it's a limit of infinity 1 over x to anything, it's equal to 0.
As long as that power is positive. 1 over x
Positive.
to any positive power. Yeah. In other words,
Okay.
as long as the x term really belongs downstairs, then that thing is going to 0. Yep.
Okay, because like if it's negative, it actually ends up going up into the numerator.
Exactly. Yep. If the
Okay.
power r were negative, then really the x belongs upstairs. And so really you're not looking at 1 over a big thing. You'd just be looking at a big thing, and that doesn't work. But as long as the thing that's getting big is downstairs and the thing upstairs is a 1 or any constant really, then that ratio 1 over something really fucking big is going to be real fucking small. That's what the theorem says. And so out of this, we get to the line we had before. I've got 1 plus 2 times 0 minus 0 over 1 plus 4 times 0. And all these zeros, are 0. So this is just 1 over 1, which is 1. This is where that rule you learned in pre-calculus comes from, right? You may have even learned it in college algebra, where if you want to find the horizontal asymptote, you compare the degree of the top to the degree of the bottom. That rule comes from this fact, comes from this theorem. So I'd like to look at a slightly more challenging example if we have time. How am I doing on time here? Ooh, it's close. All right. Let me give you one harder example, and before that, I'm going to give you just one fact that I need y'all to know. It's actually a pair of facts. Some important limits. These just come from knowing the graph. The limit as x goes to infinity of the inverse tangent of x. How many know the inverse tangent graph well enough to tell me this limit? trig here at Santa Fe, notoriously weak. Here's the graph y equals arctan x. As x goes to plus infinity, arctan x goes to pi over 2. And as x goes to negative infinity, arctan x goes to negative pi over 2. This is the graph of the inverse tangent function. You got to know it. Another important one, limit x goes to positive infinity of e to the negative x. That's 0. Here's the graph, y equals e to the negative x. This horizontal asymptote is the line 0. And as a consequence, the limit as x goes to negative infinity in regular old e to the x. You can take it as a consequence, or you can think of it as its own thing. This is also 0. This is the graph y equals e to the x. So some basic graphs that happen to have horizontal asymptotes, and the limits that we can deduce from those graphs. These are things you just got to know, right? These are graphs that should be like rock solid in your head from a good pre-calculus class, but in case they're not, here they are. Let's get them rock solid. Now, before I let you go, I do want to show you one harder example where we use that renormalization trick, but we have to use it carefully. So before we go, one last example. I'll leave these up here as long as I can. I want to find the limit as x goes to positive infinity in the expression square root 2x squared plus 1 all divided by 3x minus 5. If I want to renormalize, I need to divide top and bottom by the fastest growing term. Downstairs I have an x, upstairs I have an x squared, but it's under a square root. Good website for brushing up on these graphs would be Paul's online notes. Follow the link in the modules under review material. Go to the algebra and trig review. He's got lots of graphs there. Also, Desmos, right? Just graphing these things in Desmos. Really, the best way to get good at drawing these graphs is to draw the graphs by hand. You know, take the time, make a table, draw each one of these important graphs by hand. It's not going to be that hard, but it will take you 30, 40 minutes to get a nice picture of all of these graphs by hand. And once you go through that, you'll remember it forever. Okay. I want to renormalize. The fastest growing term in the denominator is this 3x, right? In particular, this x here. Fastest growing term in the numerator is this x squared, but it's underneath a square root. So it's really only growing at the speed of like x. So here I will divide top and bottom by x. But the algebra steps here are a little sneaky because it's not easy to divide this quantity here by x. So let me show you what we do. I want to divide the top and the bottom by x. That means I want to multiply by 1 over x. In the numerator, the only way I can get this guy under that square root is by writing him as a square root. So I'll write the top as the square root of 2x squared plus 1 times the square root of 1 over x squared. Very sneaky algebra move. Downstairs, I just leave this alone. It's 3x minus 5 times 1 over x. I'm going to distribute the 1 over x downstairs. All right, so the neat trick here is rewriting this piece as this piece, which is kosher because x is positive, so the square root of x squared really is just x. Continue this over here. I can combine these two square roots as the square root of 2x squared plus 1 times 1 over x squared. And then downstairs, I can distribute my 1 over x. I'll get 3. X times 1 over x is 1 minus 5 times 1 over x. When I distribute the 1 over x squared upstairs, I'll have the square root of 2x squared times 1 over x squared is 2, plus 1 times 1 over x squared is just 1 over x squared. And then downstairs, I still just have this 3 minus 5 times 1 over x. And now, as x goes to infinity, what happens? This 1 over x squared is going to go to 0. This 1 over x is going to go to 0. So I'll have upstairs the square root of 2 plus 0 over downstairs 3 minus 5 times 0, which is the square root of 2 over 3. So these sort of renormalization tricks in the setting of a big square root can be tricky, especially as x goes to negative infinity. The thing that made this work was rewriting this piece as the square root of 1 over x squared. That gives me 2 square roots upstairs that I can multiply. All right, lets me put them together into a big square root. But to get there, I had to rewrite this piece as this piece, which is not obvious. All right, not at all obvious, but kosher, totally allowed. I want to recommend in strongest possible terms that you guys read the textbook. Okay, read section 2.6. It's a good section. They have more examples than we've had time to go over here. They have lots and lots of pictures. Those pictures will help. They discuss the special limits that we talked about. They discuss the graphs. They discuss all the theorems. So please read this book. All right, read section 2.6. It will help you. Example 5 here, I would have liked to have done something like this, but we've run out of time, so we won't be able to. But read example 5, and then spend some time on the homework problems. If you get stuck on anything, don't hesitate to ask for help. Again, today's office hour is going to be pushed back to like 4 o'clock because I have to go look at a house. When I distribute this 1 over x, Fabrice, 3x times 1 over x is just 3. And 5 times 1 over x is 5 times 1 over x. I distribute it. Yeah, so we distribute here and here. All right, I got to get running. I do have another class that starts at 11. So if you guys want to spend more time looking at these, rewatch the video. The video will be up in just a little bit. And also please look in the textbook. The textbook does have more examples than I've had time to go over here. You should look at those. But these are the main tricks. These are the main tools. And I invite you guys to ask me questions if you have any of them. Today's office hour is going to be late. So don't go looking for me there at 1, come around 4. I'll post an announcement reminding you guys, but it'll be the same link that we use for our normal Monday, Wednesday, Friday office hour. I got to get running. I hope you guys have a lovely day and a good rest of your week, and I will see you on Monday.